Chapter 4, Work and Energy. In this chapter, you learn about work, energy, and the relationship between them, which are essential concepts in understanding how objects move and interact with forces. 1. Work. In physics, work is said to be done when a force acts on an object and causes it to move in the direction of the applied force. Formula for work: work, W equals force, F times displacement, d, where 1. W equals work done, in joules, J. 2. F equals force applied, in newtons, N. 3. D equals displacement, in meters, M. 4. Theta equals angle between the force and displacement vector. Important points. 1. Unit of work. The SI unit of work is the joule, J. 1 joule is the work done when a force of 1 Newton moves an object 1 meter in the direction of the force. 2. When is work done? Work is only done if there is displacement and if the force has a component in the direction of the displacement. If there is no displacement or no force, no work is done. Examples. Example 1. If you push a box with a force of 10 N and it moves 5 meters, the work done is 1. W equals F times D equals 10 times 5 equals 50 joules, JW equals F backslash times D equals 10 backslash times 5 equals 50 joules, J. Example 2. If you push a box with a force of 10 N, but the box does not move, no displacement, then no work is done, even though you exerted a force. 2. Energy. Energy is the capacity to do work. It can exist in various forms like kinetic energy, potential energy, and more. Types of energy. Kinetic energy, Ke, the energy possessed by an object due to its motion. Formula for kinetic energy. 1. K dot E dot equals 1/2 mv2 where 1. M equals mass of the object, in kilograms, kg. 2. V equals velocity of the object, in meters per second, meter per second. Example, a 2 kilograms ball moving with a speed of 3 meters per second has kinetic energy. 1. K dot E dot equals 12 times 2 times 32 equals 9 joules, potential energy, PE, the energy stored in an object due to its position or configuration. Gravitational potential energy is the energy an object possesses due to its height above the ground. Formula for potential energy. 1. P dot E dot equals mgh where 1. M equals mass of the object, in kg. 2. G equals acceleration due to gravity, 9.8 m/s29.8 / text meter per second to the power of 29.8 meters /s2. 3. H equals height, in meters, m. Example, a 5 kilograms object raised to a height of 10 meters has potential energy. 1. P dot E dot equals 5 times 9.8 times 10 equals 490 joules, JP equals 5 times 9.8 times 10 equals 490. Other forms of energy. There are other forms of energy, such as thermal energy, heat, chemical energy, electrical energy, and nuclear energy. 3. The law of conservation of energy. The law of conservation of energy states that energy can neither be created nor destroyed, but it can only be transformed from one form to another. The total energy of an isolated system remains constant. Example, pendulum. Example, in a simple pendulum, when the pendulum is at the highest point, it has maximum potential energy and minimum kinetic energy. It momentarily stops at the peak. As it swings down, potential energy converts to kinetic energy and vice versa. Example of energy transformation. 1. A roller coaster at the top of the track has maximum potential energy. 1. As it descends, this potential energy is converted into kinetic energy, increasing the speed of the roller coaster. 2. The total energy remains constant throughout the ride, ignoring friction. 4. Power is the rate at which work is done or energy is transferred. It tells us how quickly work is being done. Formula for power, P equals W/T where 1. P equals power, in watts, W. 2. W equals work done, in joules, J. 3. T equals time taken, in seconds, S. Units of power. 1. Unit of power, the SI unit of power is the watt, W. 1 watt, W, equals 1 joule per second. Examples, example 1, if a motor does 100 joules of work in 5 seconds, its power is 1. P equals 1005 equals 20 watts. Example 2, a 60-watt light bulb uses 60 joules of energy every second. This tells us the rate at which energy is used by the bulb. 5. Work energy theorem. The work energy theorem states that the work done on an object is equal to the change in its kinetic energy. W equals delta Ke equals K dot E dot final minus K dot E dot initial. If an object with an initial speed of 5 meters per second and mass 2 kilograms speeds up to 10 meters per second after work is done on it, the work done is equal to the change in kinetic energy. Initial K equals 12 times 2 times 52 equals 25. Final K equals 12 times 2 times 102 equals 100. Work done equals 100 minus 25 equals 75. 6. Work done by a variable force. When the force applied to an object varies with its displacement, the work done is the integral of force with respect to displacement. This concept is more advanced, but a simple case can be explained using the work done by a spring force. For a spring, the force is proportional to the displacement and is given by Hooke's law, F equals minus kx where 1. K equals spring constant. 2. X equals displacement from the equilibrium position. The work done in stretching the spring is W equals 1/2kx2. Summary of key points. 1. Work is done when a force causes an object to move in the direction of the force. 2. Energy is the capacity to do work, and it exists in various forms such as kinetic, potential, thermal, etc. 3. Conservation of energy can neither be created nor destroyed, it can only change forms. 4. Power is the rate of doing work or transferring energy. 5. Work energy theorem, the work done on an object is equal to the change in its kinetic energy. This chapter introduces you to the fundamental concepts of work, energy, and power, which are vital for understanding how things move and interact. The concepts of conservation of energy and power are especially useful in everyday applications like engines, machines, and even in simple mechanical processes. Feel free to ask if you need more clarification or examples on any topic.